Good evening, and welcome to our special report on the cosmos. Today, we're diving deep into one of the most profound questions humanity has ever asked. How did the universe begin? Recent advancements in astrophysics have shed new light on the initial state of the universe, revealing astonishing insights about the moments just after the Big Bang. Scientists are continuously unraveling the mysteries of our origins, and what they've found is nothing short of extraordinary. From the cosmic microwave background radiation, which provides a snapshot of the early universe, to the formation of the first stars and galaxies, researchers are piecing together a grand narrative of cosmic evolution. This exploration is not merely academic, it has implications for our understanding of dark matter, dark energy, and the future of our universe. In a groundbreaking study published just last month, astrophysicists reported new findings about the density fluctuations that led to the formation of galaxies. These insights challenge previous theories and open up exciting new avenues for research. As we embark on this journey through time in our video today, we'll explore the conditions of the early universe, the pivotal moments of cosmic development, and what they mean for us today. So, stay tuned as we unravel the mysteries of the universe's beginnings and discover how everything we know came from that incredible moment of creation. Let's get started.
Imagine a time before time, a place where everything we know, even space itself, was compressed into an infinitely small point. This is the mind-boggling starting point for our exploration of the universe's origins. A journey that takes us back billions of years to the very birth of existence. We're about to embark on a cosmic adventure, delving into the Big Bang theory, the prevailing scientific explanation for how our universe came to be. Our quest begins with the understanding that the universe as we observe it today is not static. It's constantly expanding, with galaxies moving away from each other like dots on an inflating balloon. This observation leads us to a profound realization. If we rewind the cosmic film, we arrive at a point where everything was much closer together, incredibly hot and dense. This is the essence of the Big Bang theory. It's important to remember that the Big Bang wasn't an explosion in the traditional sense. It wasn't an event that happened at a specific location in space. Instead, it was the rapid expansion of space itself, an expansion that continues to this day. As we delve deeper into the Big Bang model, we'll uncover the fascinating story of how our universe evolved from this initial state of extreme heat and density into the vast and complex cosmos we see today. The Big Bang theory tells the story of the universe from its earliest moments, a time when everything was concentrated in an incredibly hot, dense state. This was a period of unimaginable density and temperature, where the laws of physics as we know them were pushed to their limits. Imagine a state so extreme that our current understanding of physics struggles to fully describe it. The conditions were so intense that even the most advanced theories we have today can only approximate what happened. This primordial soup, often referred to as a singularity, contained the seeds of everything we see around us today: galaxies, stars, planets, and even life itself. It was a singular point where all the matter and energy of the universe were compressed into an infinitesimally small space. Around 13.8 billion years ago, this singularity began to expand rapidly in a phenomenon we call the Big Bang. This marked the birth of our universe, setting into motion the cosmic dance that continues to this day. It wasn't an explosion in the conventional sense, like a firework going off in the night sky. Instead, it was a rapid expansion of space itself, a stretching of the very fabric of the cosmos. Instead, it was the expansion of space itself, stretching and carrying matter along with it. This expansion continues even now, with galaxies moving away from each other as space itself grows. Picture an inflating balloon with dots drawn on its surface. As the balloon expands, the dots move farther apart, much like galaxies in our expanding universe. This analogy helps us visualize how space itself is expanding, carrying galaxies along with it. In the first fraction of a second after the Big Bang, the universe underwent an extraordinary period of inflation, expanding at an unimaginable rate. This inflationary period was crucial in shaping the large-scale structure of the universe. This rapid expansion smoothed out any initial irregularities, setting the stage for the formation of the large-scale structures we observe in the cosmos today. Galaxies, clusters, and superclusters all owe their existence to this early period of inflation. As the universe expanded, it also cooled, allowing energy to convert into fundamental particles and forces, following the principles of Einstein's famous equation, E equals mc squared. This cooling process allowed the universe to transition from a hot, dense state to a cooler, more stable one. The Big Bang Theory provides a framework for understanding the evolution of the universe from its earliest moments. It explains how the universe has evolved over billions of years, from a hot, dense state to the vast, complex cosmos. It's a story supported by a wealth of observational evidence, from the cosmic microwave background radiation to the abundance of light elements in the universe. These observations provide a snapshot of the universe in its infancy, offering clues about its origins and evolution. As we journey further into the heart of the Big Bang, we'll explore the fascinating processes that shaped the universe into the awe-inspiring cosmos we know today. From the formation of the first atoms to the birth of stars and galaxies, each step in this cosmic journey has left an indelible mark on the universe. In the first fleeting moments after the Big Bang, the universe was an inferno, a seething cauldron of energy where temperatures soared beyond trillions of degrees. In this extreme environment, matter as we know it couldn't exist. Instead, energy reigned supreme, constantly transforming into a swirling dance of fundamental particles and their antiparticles. Imagine a cosmic ballet where particles are constantly being created and annihilated, their fleeting existence governed by the laws of quantum mechanics. Quirks, the building blocks of protons and neutrons, collided with their antimatter counterparts, releasing bursts of energy that further fueled the chaotic dance. Photons, the particles of light, bounced around in a dense fog, constantly interacting with the energetic particles around them. As the universe continued to expand and cool, the energy density decreased, and the delicate balance between matter and antimatter began to tip. For every billion or so particle-antiparticle annihilations, a tiny excess of matter survived. This slight imbalance, a cosmic quirk that remains a mystery, ultimately led to the matter-dominated universe we inhabit today. The early universe, though chaotic and extreme, was governed by the fundamental laws of physics. As we'll see, these laws operating in this primordial soup set in motion a chain of events that would ultimately lead to the formation of stars, galaxies, and all the celestial wonders that fill the cosmos. Section 4. From Simplicity to Complexity, the Dawn of Matter. As the universe expanded and cooled, a remarkable transformation began to unfold. This cooling process was essential, as it allowed the universe to transition from a state of pure energy to one where matter could begin to form. The primordial soup of energy and particles started to condense into more familiar forms of matter. This soup was a chaotic mix of quarks, gluons, and other fundamental particles, all interacting in a high-energy dance. This transition marked a crucial step in the evolution of the cosmos, setting the stage for the emergence of the complex structures we observe today. Galaxies, stars, and planets all owe their existence to these early moments of matter formation. Around 1/1,000,000th of a second after the Big Bang, the universe had cooled enough for quarks, the fundamental building blocks of matter, to combine and form protons and neutrons. These combinations were not random but followed the precise rules of quantum chromodynamics. These particles, the very heart of atoms, would eventually become the building blocks of stars, planets, and even our own bodies. The formation of protons and neutrons was a pivotal moment, as it set the stage for the creation of atomic nuclei. However, the universe was still too hot for these protons and neutrons to hold on to electrons, the negatively charged particles that orbit the nucleus of an atom. The intense heat kept electrons in a free state, unable to settle into stable orbits. Instead, electrons zipped around freely, constantly colliding with other particles in a dense, opaque plasma. This plasma was a seething, turbulent mix, where particles were in constant motion and interaction. This plasma, resembling the state of matter found in the core of our sun, prevented light from traveling freely, making the early universe a rather dark and turbulent place. The universe was in a state of flux, with energy and matter constantly interacting. The formation of protons and neutrons from the primordial soup of quarks marked a significant step towards a more structured universe. This process laid the groundwork for the eventual formation of atoms and molecules. It's a testament to the power of simple physical laws operating under extreme conditions. ultimately giving rise to the building blocks of all matter. These laws, governing the interactions of particles, have shaped the universe from its earliest moments to the present day. As the universe continued to cool, it eventually reached a point where electrons could combine with protons and neutrons to form neutral atoms. This event, known as recombination, allowed light to travel freely for the first time, leading to the creation of the cosmic microwave background radiation we observe today. With the formation of neutral atoms, the universe became transparent, and the first light could shine through. This light would eventually lead to the formation of the first stars and galaxies, marking the dawn of a new era in the cosmos. Section 5. Forging the elements. The universe's first alchemy. In the first few minutes after the Big Bang, a remarkable process known as Big Bang nucleosynthesis took place. This was a period of intense transformation, where the very building blocks of matter began to form. During this brief period of cosmic alchemy, the universe's first light elements were forged from the primordial soup of protons and neutrons. These particles collided and fused in a dance of creation, giving birth to the first elements. This process, driven by the intense heat and pressure of the early universe, laid the foundation for the chemical diversity we observe in the cosmos today. The extreme conditions were crucial, as they provided the necessary environment for these nuclear reactions to occur. As the universe cooled, protons and neutrons began to combine through nuclear fusion, the process that powers our sun. This cooling allowed for more stable formations of elements, setting the stage for the universe's evolution. First, protons and neutrons fused to form deuterium, a heavy isotope of hydrogen. Deuterium was a critical stepping stone in the creation of more complex elements. Deuterium nuclei then combined with each other and with protons and neutrons to form helium, the second lightest element. This fusion process was a key milestone in the universe's early development. This process of nuclear fusion released tremendous amounts of energy, further contributing to the heat of the early universe. The energy release played a significant role in shaping the universe's early conditions. However, Big Bang nucleosynthesis was short-lived. This phase lasted only a few minutes, but its impact was profound and lasting. As the universe continued to expand and cool, the density and temperature dropped below the threshold required for further nuclear fusion. This cooling marked the end of the universe's first alchemical phase. The Big Bang left the universe with a specific composition of light elements, primarily hydrogen and helium, which are the most abundant elements in the universe today, with trace amounts of lithium and beryllium. These trace elements, though less abundant, played a crucial role in the chemical evolution of the universe. This primordial abundance of elements, predicted by the Big Bang theory, has been confirmed through observations of distant galaxies and ancient stars. These observations provide a window into the universe's past, providing compelling evidence in support of this remarkable cosmic event. The alignment of theoretical predictions with observational data strengthens our understanding of the universe's origins and the processes that shaped it.